The next thing we need to talk about is rotational kinetic energy. Anytime an object is either going in a circle or rotating, it has rotational kinetic energy. So if we want to find an expression for the kinetic energy of rotation, let's once again think about the simplest case we can imagine for rotational motion, which is an object going in a circle. So if we have an object that's going in a circle, we know generally that kinetic energy is equal to 1/2 mv squared. If we want to write this in terms of rotational quantities, we know that the velocity is equal to r omega. So we're assuming here this is a tangential velocity. If we plug r omega in for the velocity, we see that we get 1/2 m r squared omega squared. But then this mr squared quantity we recognize. We recognize this as being the moment of inertia for an object going in a circle. So we can replace the mr squared with moment of inertia, and we see that kinetic energy is equal to 1/2 moment of inertia times omega squared, times the angular velocity squared. Now we derived this expression for a single object going in a circle, but it turns out that this expression is generally true. If you have an object going in a circle or an extended object that's rotating, 1/2 times moment of inertia times the angular velocity squared is equal to the rotational kinetic energy. So rolling objects have both rotational kinetic energy and translational kinetic energy. They are rotating, so they have rotational kinetic energy. That's the energy of their spin. And they have translational kinetic energy because they are moving with some velocity from one place to another. So if you want to find the kinetic energy of a rolling object, you have to add together the kinetic energy, the translational kinetic energy, which is the kinetic energy of its movement from one spot to another. So here the v refers to the velocity of the center of mass, plus 1/2 I omega squared for the rotational kinetic energy. And so when you do problems where you can conserve energy, both of these types of kinetic energy must be taken into account. So here we see that if you have some work being done by non-conservative forces, such as friction, that's equal to the change in the total kinetic energy, both kinds, plus the change in any potential energy. So here's another question. Let's say we have two spheres. One is hollow and one is solid, and they are rotating with the same angular speed around an axis through their centers. Both of these spheres have the same mass and they have the same radius. So which sphere has the higher rotational kinetic energy?